I'm Dennis. I work at Sandia Labs, New Mexico. And today I'm going to talk about CTADL, which is a static analysis tool that I've been working on for a couple of years now. Okay, so CTADL is a taint analysis tool. So first I'm going to talk about the problem of taint analysis. So, right. So in taint analysis, what you care about is answering questions like this. Oh, geez. There we go. Okay. You're looking at some code, and user input comes in, and some sensitive sink that you're interested in answering the question, can I get data from where it comes into the system to this execute, right? Because if you can, then there may be a problem. This code might be vulnerable. So for the purposes of this talk, I'm going to refer to these as sources and sinks generically. I'm going to talk about going backward and forward in this problem, but this is kind of the framing of the problem. So taint analysis, or information flow analysis, has kind of a long history in academia, but it answers questions of this form. And why would we care about answering questions of this form? Because it's fun, but also because it answers questions like this. I found a place in my software where a secret key is being held. Does it go to a log file, right? That might not be a trivial question to answer, because you might need to follow various data flows. There might be indirection. There might be different ways that data could leak out. So you're interested in answering that kind of question. Another version of it is data is coming into the system, and it ought to be sanitized before it gets processed by a database, for example, before commands get executed, stuff like that. So this is also a question of that form. So CTADL was developed to kind of reason about these questions, and it looks at them in the following way. Sources of data are whatever you would like. You can kind of tag whatever you'd like in the system to say, I'm interested in data that comes from the database and where it flows. And sinks are similarly whatever you're interested in. You have to tell CTADL, hey, I'm really interested in data that gets written to files. And then what CTADL does is it tracks data as it flows throughout the system through assignments, function calls, and sanitizers and things like that, which I'll mention briefly. And then what you want to get from it, and what it tries to give you, is paths from those interesting data points as they come in all the way to sinks. Why would we do this, right? I've told you why the problem, I think, is interesting, but there are other taint analysis systems. So for example, for Android, taint analysis has been investigated for many years. You have systems like Mariana Trench, which is developed by Facebook, that does taint analysis. You have systems like Infer, also developed by Facebook. The main reason why we developed this is that these systems are very, very hard to modify. Static analysis is hard to work with. In general, you generally need to kind of tailor it to the problem that you're looking at. And it's very hard to tailor 180,000 lines of OCaml, at least for me. I've tried. So we developed a system that uses a different language called Datalog, which I'm going to talk about a little bit in this talk. And that is what enables us to modify the analysis in a safe way. You don't have to worry about all kinds of like complicated invariants. You don't have to worry about breaking the code as much, because you can develop an equational kind of spec for what you want to do and just add it to the system. Yeah, that's what I just said. Right. So yeah, okay. What are the other constraints that we're under kind of like thinking about developing this system? We want it to be scalable. It should process real code. So I wrote that as millions of instructions, but some of the taint analysis systems, they process some like relatively small pieces of code. We wanted to be able to process millions of instructions. It should be possible to analyze libraries and take that analysis and lift it into the rest of your analysis. I'll talk about why that is. Probably one of the most important things is that it should be visualizable. I remember when I worked on the first version of this system and kind of looked at the results, and I was like, man, this is really, really cool. I want to show somebody else. And they were like, what am I supposed to even look at? And it's like, they just don't care, right? Unless you can actually visualize the results on top of code that people want to look at. And it shouldn't have too many false positives or false negatives. I'm going to talk about that at the end. OK, so CTADL exists. It's on GitHub. You can go download it and run it. It supports Java bytecode, Android DEX, and binaries, arbitrary binaries using Ghidra. I'll talk about that in a minute. It supports analyzing multiple languages kind of at once. So you can analyze native code with the P-code component, the Ghidra component, and you can analyze your Android bytecode together if you want to. It has a very small reference implementation. So the actual core of the reasoning is 150 lines of data log, which is something that you can relatively easily understand. I'm going to show it on the next slide. The actual implementation is around 7,000 lines of code. Compare that to 70,000 or more. It's a lot easier to understand what's going on and to modify it with confidence. And it outputs a variety of things. Probably the most interesting one, I think, for this audience is Serif. So Serif, if you're not familiar, is the static analysis results interchange format. Basically, it is a format that's JSON that says, like, if I have a finding, it allows you to describe that finding in a way that, for example, VS Code and other people can load. It's an open standard. OK, so this is CTADL. Are there any questions? OK, let's. Sorry? Yeah, right. Yeah, that's right. OK, so I'm going to talk about how CTADL works. That's what I decided to talk about today, and then talk about what it looks like to use it. OK, so the usage model for CTADL, it's a command line program. And it has basically 3 steps. You start with the code, for example, a binary or an APK. And you load that in the import step. And what that does is it just creates like CSV files for all of the code that it's looking at. There's one nice thing about this is that that can be ingested very easily in other things, right? So the work of disassembly and all that stuff is done by either Ghidra or JADX or something like that. So are you all familiar with Ghidra? I'm going to say yes. JADX, if you're not familiar, is a reverse engineering environment for Java, including Android apps. OK, the next part of the process is that you, I think I have a laser pointer here, is that you can index that code, right? And what that does is it creates a global data flow graph of the whole system. So this is now independent of the question you want to ask. It doesn't matter what question you want to ask, you got to index it. And these graphs can be useful sometimes, but their main purpose is to be able to answer queries. So queries are where you specify, I'm interested in these sources, I'm interested in these sinks, and I want you to find paths between them if they exist. So that's the usage model. OK, so to kind of explain what's going on under the hood, which I think is a good kind of background, especially if you want to add something to it, is a language that is very, very simple. So this is a language in which we express the program that you're going to analyze. So in that import step, it's going to translate things into this language. And the language just has assignments, which can have fields. And it has function calls and sources and sinks. That's it, right? So in real languages, they do things like read from global variables and call all kinds of different method calls and things like that. We just have this distilled, like, very simple thing. On the right-hand side, I have an example. And just so we're on the same page, this example has a path from source to sink. So the source, what this means is that D is the data I'm interested in. And it comes from a file, because I'm telling you it comes from a file. And if you follow this yourself, you're going to see that call source is called from here. It kind of flows through this function id, and then goes to call sink. Sink has the data. And this just says, I'm interested in data that flows here. So I think you can kind of convince yourself that this does have a path. We want to be able to find this. I'm just trying to explain how this happens under the hood and then why it's scalable. OK. Right. So there's 3 steps to reasoning about this data flow. The first one is that we explicify the field accesses, which I know is a word I made up. This stuff over here, you can ask questions if you like, but I'm not going to explain too much of the syntax. This is just to prove to you this is real code. This is the actual code of the reference implementation written in Datalog. It's very, you can think of it like a database. Oh, I'm sorry. Let's go back. Yeah. You can think of it like a database. So this is just a table that has these columns. Symbol is just a string, varchar, whatever you would like. And, sorry, these are all strings. Yeah, symbol, variable, path. Number is not a string. It's a number. I'm not going to go too much into the details, but we can talk about that if you want. OK, so the first thing we're going to do is take the field accesses of the program and make them explicit. Basically, what that means is we need to understand how each assignment, manipulates fields and enumerate those splits. So let me just show you on the example. So, this was my example. Yes, let's go back. OK. Yeah, so basically we have a procedure that goes through and says all of the fields that we're going to reason about can be split up in the following ways. Apply those in the engine to reason about them. You'll see as we work through the example. OK. We're going to take all, we want to track data flows, right? So under the hood, we're going to build this like little graph tracking the data flows. So first of all, we just need to know what all the parameters are. All the variables in all of our functions flow to themselves. Very, very simple. The next thing that happens is fields. So we have this data A. We have a rule that reasons about the fields using the field splits that I mentioned a minute ago. All that we're doing is adding to our now database of facts. We're saying A.data flows to B.data because of this assignment here. So just to give you the picture, there's an engine, right, that's going and it's going to look at all these assignments and it's going to incrementally build up data flows for all the functions. That's what we're doing. OK, the next thing is to figure out like what flows from each parameter inside each function. OK. There's a bunch of steps here, but it's really not difficult. So if we look at id, P flows to Q. Great. So we record that. Q gets returned. So we record that. We do the same thing for main. A flows to, A flows to B. And A.data flows to B.data because we're reasoning about fields. So at the end of that, we know that P flows to the return value and A.data flows to P.data. OK, this is the last step. We're going to take what we computed and compute what are called function summaries. So for id, we figured out that P flows to Q and Q gets returned. What that means is we have now a function summary. And this is the key to the scaling of CTADL. The key is that now we know kind of the data flow behavior of this function ID, which I can't highlight anymore. That's OK. When we look at the call to ID in main, we don't have to look at ID anymore. We just reason using that summary. So So that leads into interprocedural data flow, which is the data flow between functions. Since we figured out that id flows its input to its output, we instantiate that at the call site, and that lets us infer a new assignment, a new data flow at the call site, which lets us know that B flows to B.data flows to C.data. We didn't have that before. Once we've done that, we are able to infer, we have enough information to kind of like directly follow a path from the source to the sink. We couldn't do that before because we didn't know how to reason about fields, and we didn't know what to do with function calls. But doing this takes care of all of that. OK. That's the reference implementation. And the key idea is that we build these behavioral summaries, right? Summaries about data flow for functions, and then use those at the call sites. In our implementation, we're not using the reference implementation. It's quite a bit longer. One of the nice things is, it's optimized. We use a data log engine called Souffle. Soufflé is an engine that comes out of academia, has a long history of development. One of the nice things about Soufflé is that you can write a small bit of data log and it will generate a large bit of C++, which is very optimized in terms of its data structures and execution strategy, right? So it can run in parallel. You don't have to code any of that. It can use these really fast B trees. You don't have to code any of that. You just write a little bit of data log in the style that I mentioned, and it will generate a really nice execution plan for you. We have optimized rules for all the parts of the process that I mentioned, but in addition, we have a couple of other abstractions which let us reason about more data flows than we would get just by following the direct flows. We have a somewhat fancy call graph construction, so if you're interested in that, I can talk about that later. But constructing call graphs is somewhat difficult for some languages. So for Java, for example, typically you resort to like a type-based approach where you say, okay, if you're calling a method of this type, I will call all the resolvents of that method. We have a hybrid method that can give us more precision, which means fewer false positives if you're trying to use this method. I'm not going to talk about k-bounded access paths. Right, okay, numbers. We like numbers. So this is just, I went to APK Mirror or something like that and downloaded, I think the first 8 apps. I think I ran the first 10, but the last 2 didn't finish on the machine that I wanted them to finish on. So what I'm doing is just running the index step on these apps, which you can find on APK Mirror. They're all Android apps. And this is the original size of the app. So we have it all the way from a couple of megabytes to 267 megabytes, which is split into resources, some of its code, some of its images, or whatever. But this is a reasonable size for how much code information is in each of those apps. That's the facts column here. So you can see that some of the even though even though this is smaller in terms of megabytes, it has more code to reason about than, I'm not going to pronounce that. Okay. Right, so in the middle column here, runtime, this is just the amount of time in seconds it takes to do the indexing. So this is that step that I talked about. It builds the global data flow graph. And this is how much RAM it took. So some of the analyses take quite a bit of RAM. This is not something you're running on your desktop necessarily, or on your laptop, I mean. Depends on your desktop, I guess. But they can still run within a reasonable amount, I think, a reasonable amount of space. And then this is just some statistics about the data flow graph that's produced. This is how many functions are found to analyze, how many raw instructions, and then once we run the analysis, it produces more instructions and more nodes, so this is the counts for those. I think overall the point of this is that we can analyze real code that you can just download without modification as long as you have enough RAM. Okay. All right, so how do you actually use it? What does it look like to use this? This is VS Code using, this is actually stock VS Code. So once you run CTADL, you get, for example, for a Java app, you get an output directory of decompilation, and you get, when you run a query, you get a serif file. So if you load the serif file in the serif plugin, you get a view like this, which says, I have found various paths from sources to sinks, and this is one of them. I'm going to zoom in a second, so don't worry. So what you get when you run this after CTADL has produced paths is you get things like tainted data has entered the system here, and it flows out of the return value of some call, right? And then it flows into some other function, and then it flows into the parameter of some other call. So you'll get a bunch of lines. So each one of these lines is like one of these kinds of things, right? It says, here's how you can track the data, here's the variables it flowed into, and so on. It's just an attempt to make all this explicit. And I think it's reasonably easy to follow, but I would love to have a discussion about that. This is not VS Code. This is Ghidra. So we also have a Ghidra Citadel plugin, which is part of the latest release of Ghidra. If you download it, you can tell it where Citadel lives on your system, and it knows how to run it. It knows how to highlight things. You can right-click in the decompilation, and you can say, track this variable, and hit go. And you will get highlights for instructions like this. You will also get highlights for variables. So specific variables that are tainted on those lines are here. The taint output also works on the in the graph view. So this is actually the taint graph where it says, hey, these particular nodes and these functions, which are variables, but this is just like another view of that, are also tainted. So you can use this to kind of do the same queries, but you do them all interactively through the Ghidra interface. And it manages the CLI for you. You don't have to run Citadel on the CLI. You don't have to write a JSON file, which is how you specify your queries if you use this interface. OK. So I want to kind of end on a little bit of tech that I think is something that I would be interested in talking to people about at this conference. So about the visualization, right? So I said Ghidra has a plugin, VS Code has the Serif plugin, and they work. But the issue is, Ghidra is an all-in-one solution, right? So let's think about VS Code. The reason the VS Code plugin works is that you're browsing the decompilation produced by the Citadel tool. If you use decompilation from some other thing, like if you want to use the latest JADX, it's not going to work. And the reason is that the binary analysis results are typically mapped onto a specific decompilation. They're not mapped in like this generic way. So I may be out of the loop on this. I'm interested in people's input. But it seems to me that there is a need for maybe a file format, something like that, that lets you say, I have run an analysis on a binary, and I've got these results. And those results are in terms of like offsets into that binary, right? They're not in terms of some specific decompilation. So we have addressed this problem in Citadel in the following way, is that what we actually produce from, we've modified JADX, which is a decompiler again, to produce this file format that looks, it's just a JSON format that's kind of inspired by Serif, but it's very, very simple. And all it's doing is tying byte offsets in the Android file, for example, in the Android app that you're looking at, to lines of decompilation. And what this allows us to do is to kind of separate concerns, right? It lets us say, as a static analysis tool that works on bytecode, I can reason about that bytecode. And then as a decompiler, you can say, oh, well, which thing are you mapping it to? So this is like a source map format, if you're familiar with source maps in JavaScript. You can use it to associate multiple binary lines with a given source line, and vice versa, which is both things which happen in decompilation. So as a decompiler, if you were using this, you would be able to take, if you kept this map format inside your decompiler, you would be able to ingest results on a binary and map them to some kind of visualization in your decompiler, which I think would be very, very useful, and is something that we're trying to work with the JADX. We would like to work with the JADX team to develop. And if tools output their physical locations, then decompilers could, sorry, that's basically what I just said. So this is something that we have written. We use this format. It's something that's available. It's part of the open source release, but I'd be really interested if other developers have run into these problems when they're trying to kind of interface with other tools. Yeah. So let's return back to my original kind of like what constraints we had when developing Citadel. It can process millions of instructions. That's nice. Sometimes the RAM is a little bit more than we would otherwise like. So I talked about how function summaries are developed and how they're the core thing that kind of enables our capability. It's also a really nice thing for adding in libraries cheaply, because what you can do is analyze a library, produce all the summaries and just lift those summaries into any subsequent analysis that uses them, right? And those summaries are typically orders of magnitude smaller than the original code, which is really nice because you could then go analyze a bunch of libraries, provide a database of these summaries, and just reuse that in your analyses. I said it should be visualizable, and I talked about how we use Serif and are contributing this kind of Serif source map idea because I think it solves a problem that isn't really solved very well right now. And I also said I would get back to this, but I think you need to let me know because this is a balancing act. So so often in static analysis, if you're familiar with the area, we talk about, well, we want to have tools that are sound. And what that means to people like me is that we want to have tools that never miss a problem, right? If you're looking for problems in code, it's never going to miss one, right? And as a result, you might have false positives. Typically what that means is that you have lots and lots of false positives. And I personally and others that I know have had experience with those tools, and what they do is they take the tool and they put it over here and they never look at it again. So we're trying to walk kind of a balancing act where we know we're going to miss things that are there, but we also are not going to overwhelm with low quality information. We want to produce high quality information for people that use this to the best of our ability. And that because there's so many kind of competing trade-offs within the tool, like it's not a question I can answer, theoretically. It has to be answered kind of empirically. So if you do use it, please let us know. We have a GitHub, we have issues, we have discussions, things like that, and I'd love to talk after this. Okay. Yeah, and I don't know how to read conference descriptions, so I had a question for hunters, but if there's any other questions that people would like to ask. Oh, I should also explain. First of all, there's a team. This is joint work largely with Arlen Cox and my team with Tim and Brennan at Sandia. I should also explain this amazing thing. So one of my coworkers at Sandia a couple of years ago now put a prompt into the then nascent AI image capability for CTADL and something about, there's lots of threads that it's following or something like that. And it came with this super metal cathedral, which I love. So are there any questions?